Okay, hello. I'm Henry Gebhardt. Today I will be talking about spherical harmonic tomography and what are the challenges to applying this to emission line galaxy surveys. Most of this work has been done while I was a PhD student at Penn State, together with my advisor Donghui Zhang, and I'm now a postdoc at JPL. So thank you for having me here. First of all, my outline for the talk is I'll give some motivation for the spherical harmonic tomography, and then I'll go through the challenges of how to actually calculate spherical harmonic projections, and go through the different features that are associated with redshift space distortions in particular. What we want to do with galaxy surveys is very often we want to measure power spectra because we can measure things like baryon acoustic oscillations, we can measure the Acoustic test, we can measure the growth of structure over cosmic time, and even non-Gaussianity has effects in the power spectrum that can be very interesting to measure. And so we want to optimally extract the information from those. Now, an advantage of doing this in spherical harmonic space is that it very naturally does the radial angular separation. And so any kind of observational effects that are that depend on either the radial or the angular coordinates are more easily and very naturally modeled. For example, redshift evolution due to, say, volume effects, the growth of structure over cosmic time, evolution of the luminosity function is very straightforward to model in spherical harmonic space. Another effect is lensing. The light from high redshift galaxies as it travels to us must pass through the matter distribution associated with low redshift galaxies. And that is very straightforward to do in spherical harmonic space. So this spherical harmonic space is the way to think about it is if the observer is here at the center of a sphere, then the observable power spectrum are the CLs on a sphere, and they're really projections of a theoretical power spectrum that is typically calculated in like a Cartesian coordinate system. And so by doing spherical harmonic, we do a projection onto a sphere, and if we do this in tomographic shells of different sizes of bins, then we call it spherical harmonic tomography. Now, to do this, we need to solve integrals of this form with two spherical Bessel functions and the power spectrum, and that gives us the CLs. And so if we look at the challenges that we have here, well, we project, in terms of measuring it, well, we can use HeelPix, very sophisticated software, to measure the power spectrum, or the spherical harmonic power spectrum. But on the theory side, we need to integrate very highly oscillatory functions. These spherical Bessel functions, especially for large L, become extremely oscillatory in a very non-straightforward fashion. And so it has been rather difficult to do this, but I'm going to show you today the too-fast algorithm, which is designed to solve exactly these kinds of integrals. Other challenges with SHT is, well, the covariance matrix is non-diagonal, since neighboring bins are correlated, and nonlinear effects can bleed into the measurement on all scales. And I'm going to talk about that a little bit towards the end of the talk. So this spherical harmonic projection was quite difficult because if we look at here a kernel, say L equals 300 of these two spherical Bessel functions, it is very highly oscillatory, and as you go to higher and higher K, you need to sample extremely finely to actually measure, to actually do this projection correctly. And if you don't sample enough points here, then you get like these beat frequencies, because this is not actually what it looks like. What it actually looks like is of course, like this. So with 10,000 sample points in this particular case, that's what you need to actually sample this function precisely, and to do the integral for a lot of k's and r's and l's takes a lot of time and is computationally quite complex. And so we developed the too-fast algorithm. This is the two-point function from fast and accurate spherical Bessel transform. And it allows to do these kind of integrals very efficiently, but it can also be used for perturbation theory, where these kinds of integrals can also occur for higher order terms. And so how does it work? Just very briefly, the idea is that this integral, if you do it in logarithmic space, it becomes a convolution integral. And so a convolution in real space is multiplication in Fourier space. And so the idea is that you Fourier transform the power spectrum in log space. You multiply it by some Fourier kernel that does the convolution. And then you just invert the Fourier transform again, and that gives you the CLs. Now, in order to do this, all the complexity is in this Fourier kernel. And the way we calculate the Fourier kernel basically contains integrals over the spherical Bessel functions. And so to calculate this, we use what's called Miller's algorithm. And just very briefly to explain how it works, it depends on the recurrence relation. And this Fourier kernel, ultimately, the recurrence relation for this kernel traces back to the spherical Bessel recurrence relations that is shown over here. And the key is that in the positive direction, going from small l to large L, the arrow starts to die. So you may start with a little arrow, and typically around L of a few hundred, the arrow just exponentially grows, and that's the end of it. It's very unstable in this direction. And so Miller's algorithm starts with the idea that it doesn't actually matter with what you start. If you go from very large L and you go backwards, the arrow will die out. So it doesn't matter with what you start. The arrow will always die out, and you can very accurately calculate this Fourier kernel, which we call M in this case. So anyway, that solves the problem of actually projecting the power spectrum into spherical harmonic space. And the way we set up the too-fast algorithm, it also works great for the linear Kaiser effect. But the next problem now is, what about nonlinear terms? What about fingers of God? What about nonlinear Kaiser effect? And the problem that occurs with these kind of integrals here is that if we have P of k, high order k to the third or fourth terms, then this kind of integral diverges. It's not formally defined. And so how do we deal with this? And so we looked into this, and we found a solution of how to do it. And for the fingers of God result, it's actually fairly simple and fairly well-known result, actually, that it's a convolution of the CL of R and R prime with a Gaussian, for example. If you model the fingers of God as a Gaussian in Fourier space. And our method also works for other nonlinear terms. In fact, any nonlinear terms can be calculated this way. And basically just blame it on the window function. Put all these terms on the window function, and then we can do that. So what does it look like? So if we look at the here on the right, it's basically we have R and R prime for our CLs, and then and so the intensity shows what is our CL, right? In these, and so most of the power is very much here at the center and on the diagonal, where R equals R prime, so that's the autocorrelation. And as you move away from that diagonal, you get cross correlation terms. And so the further away these terms are, it dies out, they become very, very small. And so this is, and notice that if you are at a bit higher redshifts, basically there's very little change along the radial direction, like in this direction here, and all of the change is in the delta R direction, so the difference between R and R prime. And so this makes it very natural to look at a projection that cuts through here. And so let's do that in the next plot. So here we have our L, and here we have the delta R for a given R, 1000 megaparsec. And in this case, I did it in real space with no BAO. And so this is the broadband power spectrum in spherical harmonic space. And it's very smooth, gets narrow towards larger L. If we now add the BAOs, we get this effect, this kind of trilobite or ribcage plot. And so the BAOs here add these oscillations here. And that's exactly what will allow us to measure distances, because for different distances, the frequency and the exact position of these fins depends on the distance. Okay, so this is still in real space, but we also want to understand, say, the Kaiser effect. So in the Kaiser effect, we have galaxies that move towards an overdensity. And so due to the Doppler effect, that means that if the observer is down here, it means that galaxies that move away from us and towards the overdensity will appear further away than they actually are. And galaxies that are on the far side moving towards us and towards the overdensity will look closer. And so we have this pancake effect. And that increases the clustering along the line of sight. In our spherical harmonic space, this looks in the following way. So we have, if you think of the typical galaxy to be near the center of an overdensity, then galaxies move towards that. And so we have this depletion of power, this anti-correlation, just a little bit away from the diagonal, so delta R equals 0. And enhancement of the correlation when delta R equals 0. So when galaxies are close together. Luckily, the BAO doesn't move much, and so that can still be used for measuring distances. Now, that's the linear Kaiser effect. For fingers of God, they have a very different effect. Fingers of God come from like the peculiar motions that are very random, and from virialized motions that are very, very larger than, say, the typical clustering. And so you get these elongated clusters that seem to be pointing towards us. So if we look here, there are some in this image. But in spherical harmonic space, what this becomes a convolution and a blurring of our space in the delta R direction. And so instead of having a very narrow autocorrelation here at the center, everything gets just a little bit blurred here in the delta R direction, and we get this kind of an image here. And so if we want to look at an animation of what this looks like, we can do this, and this is what it looks like. So we go from very small L to larger L, and as we go to larger R, the BAO moves towards a larger L, so smaller angular scales. And this includes so the Kaiser effect that depletes removes the correlation here and turns into an anti-correlation, and the fingers of God that blurs it on these scales. Okay. All right. One point to make here is that nonlinear effects can bleed onto all transverse scales. So if we look here, here's the ratio of the CL power spectrum divided by the real space version of this. And in blue is just, if we only include linear Kaiser effect, the linear Kaiser effect affects the large scales, but not at all the small scales. But if we now consider fingers of God as well, then we can see that there's a suppression on all scales, in fact. And this comes from the fact that, well, we chose a thin bin of only 8 megaparsec thickness. And so we have galaxies coming in from neighboring, from just outside that bin, that are due to the Doppler effect, just moved into the bin, and other galaxies that are moved outside of the bin. And that creates this suppression on all transverse scales. So that's something to keep in mind. Of course, this effect becomes smaller as your bin size increases. Yeah. Okay, and we also tested this with log-normal simulations. They're not perfect for fingers of God in particular, but they do work, they do include it. And so on the left side, we show the CLs. And so here in blue and green is the real space from that simulation, with the shaded being an estimate for the error bars. And in red, we have here the with RSDs, both linear Kaiser and Gaussian fingers of God in this case. And we included it both with a fit, like a theoretical prediction for the strength of the fingers of God effect, as well as a fit in dashed here. And perhaps more clear to show this is by showing the ratio of these various CLs. And so in blue is just the ratio of the measurement of the log-normal to the theory in real space. In green is the same ratio of the log-normal mux to the theory, but now in redshift space. You can see they match fairly well. And then in orange we have we only consider the log-normals and take the ratio of the redshift space to the real space log-normals. And the same in the solid red is for the theory. So we can see that, okay, it doesn't match perfectly, but it is a decent match to the log-normal simulation. Okay, and with that, I will leave you with the conclusion and future outlook. I hope I have convinced you that spherical harmonic projection is interesting to look at, and that we can calculate it theoretically fast enough. We understand how like a phenomenological fingers of God effect and how the Kaiser effect enters the spherical harmonic tomography. And we do need to be aware of that if the bins are very small, then nonlinear effects can bleed onto all the scales. And so that's something to keep in mind when applying this kind of method. And so in the future, I hope to include more nonlinear terms and apply it to actual data. Thank you.